Pre-calc lecture for lesson 119, Descartes rule of signs, upper and lower bound theorem, and irrational roots. So if you read all this, you should read all this. It's very interesting. But basically it's telling you that we have a way of finding out how many roots, how many positive real roots, and also how many negative real roots are in a polynomial without having to find out what the roots are. So the way to do that, oh, and there's something else that it talks about. Sometimes we have real roots and also imaginary or complex roots. So the complex roots sometimes also cause a sign, what we call a sign change in the polynomial. So I think the best way for me to do this is just to kind of show you how to do one of these. So down here it says the number of positive roots of a polynomial equation with real coefficients equals the number of sign changes in the polynomial, or that number minus 2, minus 4, minus 6. So what does that mean? I'm going to go ahead and just do a problem for you because I think it's a lot easier if I just explain it. I'm going to do 119 number 6. Okay, so it gives me this polynomial. It gives me x to the fourth minus 2x cubed plus 3x squared plus 4x minus 7. And it wants to know how many roots. And remember, roots are, this thing's a quartic, and we know that well, you might know that a quartic can have a shape kind of like that, and that if it hits the axis just right, it could have up to 4 roots, because that's what the roots are. It's where it hits the axis, the x-axis. So, I mean, we can find out how many, what the possibilities are, but this Descartes rule of signs says we can just look at the signs of each term, and that'll help us find out exactly how many roots, how many real roots it has. Because remember, we could have this situation going on. We could have it where it doesn't have any real roots, but maybe it has some pairs of complex roots. Because remember, the complex roots come in conjugate pairs. You'll have like plus or minus 3i or something like that. So count. What we do is we count the sign changes. So, and I already wrote yeses and nos on it. So the first term is positive, and so the first term is positive, the second term's negative. So I encountered a sign change, right? I went from a positive to a negative. So I wrote a y for yes. There was a sign change, so yes. This went from negative to positive, so that's a yes. This went from positive to positive, so I just wrote no. No, there's not a sign change. And this went from positive to negative, so there's yes. So there was 1, 2, 3 sign changes. So the problems are easy to do. All you have to do is say, count out how many sign changes it has. 3 changes, so 3 or 1 positive real roots. Why did I go from 3 to 1? Because there could be up to 3 positive real roots, but you know that the complex roots come in conjugate pairs. So I'm always going to, like, however many sign changes there are, I'm always going to subtract 2. So I'm going to go 3 minus 2, that gives me 1. So I could either have 3 real roots, or I could have 1 real root and a pair of complex roots, which adds up to 3, right? 1 real root and then 2 complex roots adds up to 3. Okay, so that must mean that this, let's see, what would that mean? If it hit the axis 3 times, it might, oh, that didn't hit 3 times. You could probably draw it where it hits the x-axis 3 times if you tried, right? Maybe one of them's going to bump the axis. I should have had some forethought and drawn one for you, but you can play around with that and see what it might look like. Or you can get out a graphing calculator. So this is just, so these are actually easy. The way that you do the negative roots, or if it says, like on, let's go back to your book. On 119. The number, it says on page 652, it says the number of negative real roots of a polynomial equation with real coefficients equals the number of sign changes in p of negative x. So I don't have one of those to do for you, but because you're not assigned one of those. But what you would do is plug in negative x in the original. So let's just go ahead and get some new paper. How much time do we have? We'll go ahead and, even though this isn't one of your problems that you have to do, I'm going to go ahead and find out how many negative roots, because so that was positive roots. How many negative roots? So what's p of negative x? So in other words, if I put negative x in here, wouldn't I still have x to the fourth? Because, I mean, if something's to an even power, it cancels out the negative, right? But this one, if I have negative x and it's an odd exponent, then we're going to actually have a negative x over here and that negative, so we're going to have positive 2x cubed. Here's an even power, so we're going to have, I'm just plugging negative x in. I'm kind of doing it in my mind. 4 times negative x would be, count the sign changes. That's not a sign change. That says no. That's not a sign change. That is a sign change. That is not a sign change. So then I would say 1 sign change so exactly, right? Because if I subtract 2 from the 1, I'm going to have a negative number. So then there's not going to be a negative number of roots. So exactly 1. Oh, hey, that makes sense. 1 negative real root. Now, you weren't asked to do this. I just wanted to show it to you. So that kind of makes sense, though, because we just found how many positive real roots. And remember I was saying, oh, here, try to figure out how to draw that. Well, we know that there could be 3 or possibly 1 positive real root. Well, we're going to have exactly 1 negative root. So let's see. So there could be a negative 1 over here, and then 3 positive ones. You know what I mean? So like on here, if I just draw my axis, look at that. If I just draw my axis like that, there's 1, 2, 3 positive real roots and 1 negative real root. So it could look something like that. Or, I mean, there could actually be a pair of I want to say eyes, a pair of complex roots also. So that's Descartes' rule of signs. And then upper and lower bound, oh gosh. I think I'm going to make another video for upper and lower bound.